All good? Okay. So I start again then. So we're looking at the very large telescopes in Chile. The telescopes are pointed here into the center of the galaxy. Now, our galaxy is it's a thin disk, and the Earth is located about halfway towards the edge on one of the spiral arms. And so by looking into the center, we see this disk, this Milky Way in the sky. Now, if you zoom in a little bit, and with a bit of imagination, you'll be able to see the constellations of Sagittarius and Scorpio. And the galactic center is located about, somewhere in between these two, although I've taken a bit of artistic license in placing them exactly where they are. Now, if you look even closer, right, and even closer, we are going to see some interesting observations. So this is a series of images, quite raw, taken by the Keck telescope in Hawaii. And you can see some orbits. What you're seeing are stars right in the center of our galaxy. And these stars are orbiting something, right? This is an extremely interesting system to study. And I'm going to go to the next slide, which is going to take us a little bit away from the rawness of this image into something slightly more reconstructed, slightly cleaner, but still directly from these observations. This is work that was done over a period of about 30 years by two teams, the American team using a telescope in Hawaii and the German team using a telescope in Chile. These stars are orbiting something, and these stars are orbiting something extremely fast. In fact, some of them get up to a few percent of the speed of light while they're doing this. So the gravitational field is extremely strong. And their orbits, although they look like ellipses, they're not quite ellipses. We understand Newtonian gravitational theory extremely well for a very long time, and it's been able to explain almost all gravitational phenomena, but something is wrong with it, and that theory does not work when we look at this picture. So not only are these orbits actually in very strange shapes, but they're orbiting something that we can't see, something that's black in the center there. We don't know what that is. Is it a collapsed star? Is it some kind of neutron star that emits no light? Is it a form of dark matter? Is it something that we haven't even thought of before? On the top left, you see Andrea Ghez. In the middle, it's Reinhard Genzel and Roger Penrose in the top right. Andrea's instrument, the telescope, you see in the bottom left, that's the Keck telescope in Hawaii. Reinhard's, you see in the bottom. And Roger Penrose, who I've not really mentioned yet, he's a theorist, which means unlike the other two who are observers, Roger's tools are mathematics and I guess a couple of doses of imagination. So Roger really brought our understanding of the geometry of space-time under extremely large gravitational fields into perspective. And he helped us understand and developed a lot of the mathematics, which help us understand how objects move in such space-times. Now, if you apply some very, very basic ideas to the orbits of the stars that I show you, you learn that you will see that in the center, the only way the stars could be moving so fast around this common center is if something was there that we don't see, right? Something was there that has a mass of about 6 million times the mass of our sun. So it's something extraordinarily massive and powerful, and yet we don't see it, right? We're going to take a bit of a different perspective. So we take a step back now, 100 years or so. This is a young Einstein. You don't usually see Albert Einstein so young in images. And I took it because I guess this is about how old he would have been when he started thinking about the general theory of relativity, the new description to how gravity works. Einstein has many, many achievements. I certainly think he discovered so much, and certainly his most profound work was in the theory of gravitation. Einstein looked at Newtonian theory and he thought, this just doesn't make sense. It's going to break down, and he found so many inconsistencies. And he replaced the theory of general relativity, of Newtonian gravity, with the theory of general relativity, a new theory of gravitation. There are a lot of things, a lot of consequences out of this equation. And on the left-hand side, you see these R's and the G's, right? On the right-hand side, you see the T. It's deceptively simple like this. There are just a few letters here, right? But there are 10 equations in there, and if you expand them further, you'll fill many, many, many pages just with the equation before you even start to work with it. They're very difficult to solve. But they work very well in describing early universe cosmology, describing the formation of the universe. Everything that's got to do with gravity is very well explained by this equation. In the 1960s, a mathematician physicist called Schwarzschild, he found a unique solution to this equation, which was considered a mathematical fantasy at the time, something that we cannot have in reality. And like if we look again at these equations on the left hand side, the R's and the G's, they encode the curvature of space-time. And on the right hand side, you see this T mu nu. This is the energy momentum of space-time. And what it says here, this equation, is that the energy momentum of space-time curves space-time. And in turn, the curved space-time, which is a gravity, really tells energy and matter and momentum how to move. So that's very key. I'm going to say it again. Energy momentum curves space-time, and curved space-time tells energy and momentum and mass how to move. Now, the unique solution that I was referring to earlier to these equations from Schwarzschild made no sense at the time. He found a solution in which a spherical region of space had a gravitational field so powerful that no light could escape. It didn't really make sense to people. We don't see anything like this. It's probably just a mathematical artifact, whatever. A lot of theoretical work was done on that. It was a very interesting space-time to discover, to work with, at least from the mathematical perspective. But yeah, and I mean, this thing is called a black hole, right? What I'm talking about, you might have heard of it. So the solution of a black hole region of space-time that's so powerful and no light can escape. I've put an image of it on this slide, right? I'm being a bit facetious now because that's exactly it below the equation, right? Is nothing. Right? When you look towards the center of the galaxy, the common center around all of these stars, you also see nothing, right? I've taken a bit of artistic license here. This is a computer-generated image of the space-time surrounding a black hole with an accretion disk, where you have a lot of very, very hot matter getting sucked into this region. And the silhouette that this matter makes as it radiates away its energy, you can see in the picture. So that the dark center is the black hole. But if you look into the galactic center, right, where all the stars are, you see nothing. Now, obviously, you know what I'm getting at. Through these observations by these scientists for many years, right, 30 years, studying the shape of these orbits, studying the frequency of the light, the color of the light that arrives in our telescopes of these stars as they approach this extremely strong gravitational field in the galactic center. This has unequivocally now culminated in pretty much perfect, extremely strong evidence for the correctness of these equations. And before this, we had many reasons to doubt that this fundamental theory of gravity is ultimately correct. And there are other theories of gravity that are even more complicated than this, and it turns out they're all wrong, right? And this is the one that works. It's written down 100 years ago, and it's the work of these scientists, as well as perhaps a few other discoveries in the past years that have really solidified this into correctness. I'm going to keep it local, right? Einstein worked in Zurich, German origin. So he worked in Zurich for a while. But we're going to jump forward 100 years to 10 years ago. So University of Zurich was involved in part of this work. So I worked with Prasenjit Saha, a professor at the University of Zurich. And we are theorists. We don't know how telescopes work very well. We worked on the orbits of these stars, and we studied them from a theoretical perspective. We computed the consequences of the general theory of relativity and other theories of gravity on this system. And in particular, we worked on how light travels in this environment of extremely strong gravity around a black hole. What you see here is a very dirty simulation that we put together, I guess, a few months into my PhD. I apologize, it's not as sexy as the images you showed earlier, but this is the way theorists work. It was hacked together at some point. You seeing a star, the blue track orbiting this black hole, the red lights are photons, little bits, rays of light that are getting absorbed by a telescope on what we see as the Earth far away there. Now, this star has been brought really, really close in. You can see that the orbit is not an ellipse, and maybe you can see right now that those rays of light are not exactly straight. Right? They're going to get contorted and lensed as they go around the black hole, and you're going to see it happen when it approaches the black hole. So it's going to, as the gravitational field gets stronger and stronger, so this is a consequence of a bunch of mathematics, some computation, and bam, there it happens. And that signal is something very particular to general relativity, right? So this is my last slide. Just a few closing points, a few final thoughts. When we worked in this field, we didn't expect that it would culminate in a Nobel Prize. Because the Nobel Prize in physics is usually given to scientists who manage to discover something, which then discovers some fundamental physical principle, which then turns into really strong benefits to humans and society. For example, the LED, right? The fundamental principles which culminated in the LED and allowing you to go to the bathroom in the middle of the night without tripping over something. They got the Nobel Prize a few years ago in physics. The original work that resulted in us being able to develop the technology for MRI machines, the discoveries of those physical principles, which has ultimately led to saving countless lives through medical diagnostic techniques. These are the people usually get the Nobel Prize. Why do we do this? There's no application here, right? At least not yet. And this is my point is that we just do science because we can, because it's fun and it's interesting, and we don't have an application for it yet. But that they award the Nobel Prize to a group of people without yet having a strong application, that's great. It's been done before for the Nobel Prize in physics, but it's not often that it's like that. Who knows, perhaps in many years in the future, before humanity doesn't manage to destroy itself before that, we'll find a way to use this and turn it into technology. How can we build from strong gravitational physics in the neighborhood of a black hole? That might be exciting. So we're very proud and very happy that this was being awarded to those three scientists. It's absolutely amazing, and of course we're proud to have been involved in a very modest, small way here in Zurich. So yeah, this animation plays on.